Hi, welcome back to Mrs. O'Graham's Maths. This is a worked solution video for the D&D resource booklet for the differentiation papers. A thank you to them for allowing me to share their resources in this way to do these worked solution videos for you. There is a link in my video description to their website. It's well worth going and ordering a set of these books for yourself and working through them on paper, and then just use these videos to help you through the solutions as and when you need them. So we're looking at the ones for paper 91578 on differentiation, and we're doing practice external assessment number 4 today. So setting off with question 1, we are differentiating the natural log of this function here. Now, to differentiate natural logs, we do 1 over the thing that's inside, so we put the 3x squared minus 2x on the bottom, and we multiply by the derivative of the inside. It's a version of chain rule. So the derivative of the inside goes on the top, so we have 6x squared minus 2x all over 3x squared minus 2. For part B, we've got an apprentice painter hired to paint the outside walls of a school, and we're looking at the volume of paint that he uses in T hours. We want to know the rate at which the volume of paint is being used when we are at the 6-hour mark. So to find rates, we need to differentiate, so we'll do dv by dt. So bringing down that 3 over 2 and timesing it by 4 gives us a 6. The power gets reduced by 1. The inside stays the same. We're doing chain rule. And then we multiply it by the derivative of the inside, which is 2/5. When we differentiate the minus 4, that differentiates away to 0. So that's our function done. Now, when t is 6, dv by dt will be equal to, well, 2 times 6 divided by 5, add 1, and then to the power of a half is we're going to square root that. Then we times it by the 6, then times it by the 2 over 5. So we get an answer of 4.43, and the volume is measured in litres, and the time is in hours, so it's litres per hour. Okay, for part C, we've got one of my favourite types of questions here. So for this first one, we want to find when f of x is not continuous. Now, continuous means you can draw the graph without taking your pen off the paper. So anywhere that we have to stop and take the pen off the paper, that's when it's discontinuous. So the first one is right here when we've got a hole in the graph. So that is happening at x equals 0. And the second one is here where we have a very significant gap in our graph, and that's happening where x is 3. For it to be not differentiable, it's anywhere that there's a gap, so anywhere that we've already said, so the 0 and 3 is going to be in there, but also anywhere where there's any sort of strange kink or turn or sharp corner in our graph. So that's this bit here at minus 3. Because we've got a sharp turn there, where our function clearly changes from one function creating this left-hand side into a different function creating the right-hand side. And when they're different like that, we can't differentiate it. Then we have anywhere where there's holes, so we had the 0 and the 3 from before. And then finally, we've got another kink just here at 7. For part 3, we want the derivative to be equal to 0. Or in other words, the gradient equals 0. So we're looking for any points on our graph that are either horizontal or they're turning points that give us maximums or minimums. So that happens just here. That's at minus 3. We've got another one. Wait, I misread that. That's not minus 3. Just that's at minus 5. Sorry for that. So then our next one where our gradient is equal to 0 is the minimum down here. That's at x equals 5. And then we also have this line here. The whole of that is horizontal, so it has a gradient of 0. So we also have it when x is more than 7 is the start of that line. For part 4, we want concave upwards. Now, I always teach my students, think about concave up and concave down as being a bowl. So if the bowl is the right way up, it's concave upwards. And if your bowl was upside down, then it's concave down. So an upturned bowl is just here. So we've got the whole of that portion, all of it counts as being concave upwards. We don't just mark the minimum point, the whole of that curve is concave upwards. It all makes part of the bowl. So that's between 3 and 7. Now for part 2, we're looking at the limit as we approach 3. Now for limits, we need things to come to the same number from both the left and the right, and for it not to be infinite. So what we're looking at 3 is as we come to it from the left-hand side, we're heading towards a value of 5. But as we come towards that point of 3, from the right-hand side, we're heading towards a value of 3. So they're not getting towards the same point from both left and right, so it does not exist. I should probably finish that properly. Does not exist. There we go. Okay, let's move on to part D. We want to know when this function is increasing. That means the gradient will be greater than 0. So let's find our gradient function first. Remembering that this is the same as 4x plus 1 to the half. So if we were to differentiate that, we bring the half down, reduce the power by 1, leave the inside as it is, times by the derivative of the inside. The second term, if we differentiate minus half x, we just get minus a half. And we need for that to be increasing so it's greater than 0. Now let's tidy that up a little bit. So 4 over 2 gives me a 2. The 4x plus 1 is on the bottom as a square root down there because we've got it to the power of minus a half. Then minus a half is greater than 0. Well, we can move the half over, so that would be greater than a half, like this. We can cross multiply, so bring the 2 up and it's a 4. Bring the root 4x plus 1 up and to the right and times it by the 1, like so. Then we can square both sides. And now if I bring the 4x, if I reverse the whole thing, actually let's do that first, then I'd have to reverse the sign as well. Just because I want the x's on the left hand side, it's going to make a little more sense. So 4x will be less than 15, so x is less than 15 over 4, or x is less than 3.75 if you need it in decimals. We've got some parametric equations for part E, so let's do dx by dt and dy by dt. So we have a 1 plus, well, square root of t is t to the half, so this will be half t to the minus a half. dy by dt will be 1 minus half t to the minus a half. So dy by dx will be dy by dt times dt by dx. So this is going to be, actually let's rewrite them as square roots and putting them on the right parts of a fraction. So this will be 1 plus 1 over 2 root t. Ooh. And this will be 1 minus 1 over 2 root t. So then we have 1 minus 1 over 2 root t. If we timesing by dt by dx, then it's the same as dividing by dx by dt. So let's put 1 plus 1 over 2 root t. I keep writing as a 2. Okay, let's pop that as all over 2 root t on the top. would give us a 2 root t minus 1. And the bottom, again, let's put it over a common denominator of 2 root t would be 2 root t plus 1, which is the same as if I was to divide by that fraction, it's the same as if I times by its reciprocal. So just what was on the bottom I'm now bringing up here. So then the 2 root t's cancel, and we get 2 root t minus 1 over 2 root t plus 1. Now let's check back in with what we're trying to do with this question. We want the second derivative, and we need to find it when we're at the stationary point. So we do need to work out where the stationary point is. So let's do that now. Set that equal to 0, and we'll end up with 2 root t minus 1 equals 0. So root t would be 1 over a half, so t is a quarter. At our stationary point, and I just have to think about the spelling there, stationary point, there we go. All right, now let's find the second derivative. Now to do second derivative, we differentiate dy by dx. This thing here, we're going to differentiate that again, and then you have to times it by dx by dt again. This one's on your formula sheet. So I'll just flick over and show you. So here's where it is on the formula sheet. If we're doing the second derivative, the bit that often gets forgotten is doing this times by dt by dx again. So we need to differentiate it again, and then times by dt by dx again. So now we've got t is a quarter. We need a function for the second derivative. So we're doing d2y dx squared. Now the second derivative we do by differentiating the first derivative and then multiplying it by dt by dx again. Remember, this was dt by dx that we worked out already. So we'll use those pieces. And again, that's on your formula sheet for doing parametric equations and finding the second derivative. One of the biggest mistakes is to forget to multiply by dt by dx again once you've differentiated this. So just don't forget that particular point. Okay, so if we differentiate this one here, we're using the product rule where u is the top and v is the bottom. So if we just differentiate each of those to make it a little easier when we put it together, so 2 root t is going to be, that's 2t to the half, so that's going to be t to the minus a half, and dv by dt, same thing actually, we're going to have t to the minus a half here. Now t to the minus a half is 1 over root t. It's probably going to be easier to have it in that form there. Okay, so this, popping that back into a square root. Okay, so we start with v du by dt. Oops, that was supposed to be a t just there. So this one here, multiply those two together. So 2 root t times by 1 over root t is just 2 plus 1 times 1 over root t. Then minus u dv by dt, so those two times together there. So we have 2 and then a minus 1 times 1 over root t. And then all over v squared, which is 2 root t plus 1 squared. Then we times it by the dx by dt, remember? Sorry, dt by dx, this one here. So that'll get times by 2 root t over 2 root t plus 1. Okay, let's tidy that up. So on the top, we've got a 2 minus a 2 cancels. 1 over root t plus 1 over root t is going to give me 2 over root t. Then that's going to be multiplied by 2 root t, and on the bottom we've got 2 root t plus 1 squared being times by another 2 root t plus 1, so now it's cubed. Okay, so on the top there, those root t's cancel, and we have 4 over 2 root t plus 1 cubed. Now, when t is a quarter, the second derivative will be 4 over 2 times the square root of a quarter plus 1 cubed. Okay, let's work that out. So 4 divided by 2 times the square root of 0.25 plus 1 to the power of 3 equals 0.5. Okay, let's get that all on one page for you so you can see the full solution all together. There we go. So the value of the second derivative at that point is 0.5. Moving on to question 2. So cot is on your formula sheet, and cot differentiates to negative cosec squared. So if we do dy by dx, the function part of it, cot, becomes cosec squared. It started off as a negative here, so now our answer will be positive. The inside stays as it is, but now we times the outside by the derivative of the inside. So if we differentiate x over 2, we get a half, so that 4 becomes a 2. Okay, so on this one, let's start by finding f dash of x. Well, e to the ax, if we differentiate that, whatever number a is, that constant there comes down to the front, so it's a e to the ax. Okay, we also need the second derivative, which will be a squared e to the ax, because we start with the first derivative. Again, the e function doesn't change, but we multiply by the coefficient of the x in there, which is, the derivative of the power. Okay, so now let's go for f dash of x minus a times f dash of x. That will be equal to, well, f double dash of x is a squared, e a to the x, minus a times a e to the ax, and you can see that's obviously a 0. On part C, we've got a little bit of kinematics. We have the displacement function s is the natural log of t squared plus 20. And we want to get to the acceleration function. Well, first we need the velocity as a middle step. So the velocity is to differentiate s. So this will be 1 over what's inside of the function there for differentiating a natural log, and then we times by the derivative of what's inside, which is 2t. And then the acceleration function is to differentiate the velocity function. Now this one is using the quotient rule, so we do v du by dx, so the bottom times the derivative of the top, looks like this, minus u times dv by dx, so that's 2t times by the derivative of the bottom, which is 2t, so we end up with 4t squared, all over v squared. What we want to know is when is that acceleration equal to 0. So let's set that to be equal to 0. If we bring that up and multiply, we'll get a 0. So we're just interested in the top part. We've got t squared plus 4t minus 4t squared would then be equal to 0. Which is 4t minus 2t squared equals 0. So 2t squared equals 40, t squared is 20, so t is the square root of 20, and it's only the positive square root because we're dealing with time since the beginning. We're not going into negative time. And if you want that in decimals, that would be, let's do the square root of 20, 4.47 seconds. Got some parametric equations for part D. So dx by dt, well, sec is on your formula sheet, that differentiates to sec tan. Dy by dt, tan squared, think about it as being tan of t squared, and then, oh, I should have written that up here, that's tan of t squared, so that when we differentiate it, you can now see it's a chain rule. So this will be 2 tan of t to the 1 times by the derivative of the tan, which is sec tan. So sec t. No, I misremembered that. I was mixing up my tans and secs. So tan differentiates to sec squared. Just use your formula sheet to make sure you don't make silly mistakes like I just did. Okay, so that would be tan t sec squared t. And writing that out in full looks more like 2 tan t sec squared t, just like that. So then dy by dt is to take the dy by dx, 2 tan t sec squared t times by dt by dx, which would be 1 over this thing here. So let's just put that, oh, let's come back. Yeah, put that as a fraction. And what we're left with is 2 sec t, because the tans cancel, one of the secs cancel. Now that is the same as 2 over cos t. So when t is pi by 3, dy by dx will be equal to 2 over cos pi by 3. So 2 divided by cos of pi by 3 is 4. We've got a tricky rates of change question for this one in part E. So let's start by writing down some information about the rates. So the trough is being filled with water at a rate of 8 litres per minute. So let's write that down as dV by dt is equal to 8. It's increasing by 8 litres per minute. The rate that we want to find out is the rate of the water level rising, which we can see on our diagram has been labelled as h. So we want to find dH by dt. Now to get dH by dt, if we start with dV by dt, we would have to times by dH and remove the dV by dividing by dV. So we need something that links the h and the v together. If we can find volume in terms of h, then we can get dH by dV. Now what's going to be tricky about this is working out the formula for the volume and making sure it's all in terms of h. So let's get cracking with that. So we need to be able to find the area of this trapezium, so we can then multiply it through by the length of the trough to get the volume of water that's in there. We need to work out the h piece, and for that we're going to need to think about this triangle. Now if I just draw that a bit bigger up here, we've got this height here. Let's call this width there an x. This angle here would be 30 degrees. Now the reason we're doing this is so we can find the full length of this piece just here, because we've got 25 here. We need to be able to add those two sides together for part of the formula for finding the area of a trapezium. So we need to be able to work out that x value in terms of h. Well, this is using the opposite and the hypotenuse. So if we're working out x, that's going to use tan. So we're finding the opposite, so that will be tan times the adjacent. So h times tan of 30 will be x. Now, tan of 30 is one of the special values on the triangles that you have on your formula sheet. Tan 30 is equal to 1 over root 3. So this whole thing is equal to h over root 3. So now the volume. So the volume of the water will be equal to the area of that trapezium. So we have 25 plus the top of that trapezium is going to be 25 plus 2 lots of what we just worked out to be this little piece here, this x piece. We'll have another one on that side as well. So we'll have 2h over root 3, like this. Once we have added together the two sides, we divide it by 2. We times by the height to get the trapezium, and then we multiply through by the length of the trough to get the area. The volume. Okay, let's tidy up what we've got here. So we'll have 25 plus 25 is going to be 50, and then divide it by 2 is 25. Then we have plus h over root 3. Then they get multiplied by h, so there's an h squared there. This becomes 25h. And then they get times by 90, so 25 times 90. Let's do this in 2 steps. Here we go. That will be 2,250h plus 90h squared over root 3. Now I've got v all in terms of h, I can do dv by dh. So differentiating that, we get 2250 plus 2 times 90 is 180, h over root 3. Okay, back to now we can work out dh by dt. Now that is dv by dt times dh by dv. Now dv by dt was what we were given in the question, but just one thing to note, we've been working here entirely in centimeters cubed, and this is in liters. Liters comes from 1 liter is 1,000 centimeters cubed, so we need to turn that into being its equivalent. So it'd be 8,000 centimeters cubed, rather than it just being a singular 8. I imagine lots of people would make a mistake on that. So this will be 8,000 times by dh by dv, which was this one here, but flipped over. So 1 over 2250 plus 180 h over root 3. So now working out when we're doing that for is when the height of the water in the trough is 12 centimeters. So when h is 12, dh by dt, we'll pop it in. So it's going to be 8,000 divided by 2250 plus 180 times 12 divided by root 3. Comes to 2.29. Now our height is in centimeters and our time is in minutes. So centimeters per minute. I'll show you that all on one screen. There you go. Okay, on to question 3. This one's a little hard to see on the digital printout here. That says x e to the pi x plus 1. So if we differentiate dy by dx, we're going to use the product rule here. we've got one piece times by another piece. So we do the first one differentiated as 1, we get e to the pi x plus 1. Add on the first one times the derivative of the second, which is to say that it's pi e to the pi x plus 1. You can leave it like that, you can tidy it up, you could factorize it, but I would just say leave it as it is and you'll get your mark. Okay, part B, we want the x values on this curve where the gradient is -6, so we need to have a gradient function first. So dy by dx is going to be 1 over x. Rewrite this as being x to the -1, and you'll see that it's going to be minus x to the -2 if we differentiate it, and then -2. We're setting that gradient to be equal to -6, as was in the question. So now that's -1 over x squared is equal to -4. So x squared is equal to 1/4. So x is going to be plus or minus 1/2. Okay, part C. Get this picture on to help us out. So imagine this picture is a bird's eye view. The ship is 5k away from the coastline point P, and there's a light on it that's sort of going around in circles like this. So it rotates around once every 12 seconds. So we'll be interested in this angle here, theta. And the light is moving inwards from the ship towards the coastline and filling up that space as it turns around. So we want to know when the light gets to be 1 kilometer away from P, so just here at 1 kilometer, then how fast is that beam of light moving? That's saying like how fast is it going around, so that's the x distance that we're talking about there. So we're trying to find dx by dt. Now what we're told about the information that we've got in terms of rates is that it makes 1 revolution every 12 seconds. So a full revolution is 2 pi. So thinking about this angle theta and how much that's changing, then d theta by dt is that one is moving at a rate of being able to do a full circle every 12 seconds. So a full circle is 2 pi. Divide it by 12 and you've got how fast it's going. So it's going at pi by 6 radians per second. So if we've got d theta by dt, let's work out how to turn that into dx by dt. So if we start with d theta by dt, we would need to multiply by dx and divide by d theta. So the other bit we need to now work out is how we can make dx by d theta. So we need something that links x and theta. Well, we've got a right-angled triangle just here. So we have x on this side over here. We've got theta. We also know the 5 that's just here. So we've got the opposite and the adjacent. So we're using tan. So tan theta is equal to the opposite over the adjacent, which is x over 5. X is equal to 5 tan theta. Now we can do dx by d theta. So this will be tan differentiates to sec squared, so this will be 5 sec squared theta, which is the same as saying 5 over cos squared theta. And I'm writing it like that so I can substitute into the calculator more easily. So if we're working out dx by dt, we will be doing d theta by dt, which is pi by 6, and multiply it by dx by d theta. I'm just using what we had up here. So now dx by d theta is 5 over cos squared theta. So this is 5 pi over 6 cos squared theta. and we need to work it out when we're 1 kilometer away from P. And I've just realized I misrepresented that on the diagram earlier. That 1 kilometer is actually in the x direction. So the light goes all the way to P and then sweeps around. So we want the rate when it travels a kilometer past P. So when we get to 1k in the x direction. So when x is 1, we need to work out what theta would be so that we can substitute it into this. So if we've got the triangle with 5 and 1, we can find theta there. So tan theta is equal to 1 over 5, which makes, if we do inverse tan of 1 over 5, we'll get theta is equal to 0.197. And that will mean we can substitute into dx by dt up here. So we'll do 5 times pi divided by 6 times cos of that answer we just had. I'm going to pop in some brackets here so that I can square that. That gets squared, cos of that thing squared. And then we've got 2.72. The distance is in kilometers and our time is per second. That was quite a tricky one to work out the context that was in and exactly what was happening. Don't beat yourself up if you struggled to get that one by yourself. Okay, part D. Quite a bit going on. Not straightforward to imagine it, but we have a curve. We've got the equation of the curve just here. We're told that we have a point on the curve that has a x-coordinate of 4. We've got a gradient of the tangent at that point is 1/3. So when x is 4, the gradient is 1/3, and we want to find the possible values of p. Now, having checked through the answers to this one, I think there's actually a typo in this question because the answers are in terms of k. So I'm going to do it in terms of k. Where we've got a lowercase p, let's turn that into a k. X cannot be equal to k. And we're finding all the possible values of k to answer this. Okay, let's carry on with that. All right, so we need to find dy by dx. Remembering that k is just a constant. Now we've got the quotient rule here, so we're going to do v du by dx, so the bottom times by the derivative of the top, which will be 2k minus x. Minus u dv by dx, so the top times the derivative of the bottom. Well, the derivative of the bottom is just minus 1, so that would become a plus 2x plus k, all over v squared, which is k minus x, all squared. So this then becomes 2k plus k is 3k, minus 2x plus 2x is 0, all over k minus x squared. Then we know at p, x is equal to 4 and the gradient is equal to 1/3. So 3k over k minus 4, substituting in for the x, is equal to 1/3. So 9k is k minus 4 squared. So let's multiply that out. We've got k squared minus 8k plus 16. K squared minus 17k plus 16 equals 0. So k minus 16k minus 1 equals 0. Therefore, k equals 16 or k equals minus 1. Nope, not minus 1, plus 1. Okay, so we have something of a rates of change question here, or rather an optimization problem, let's call it that. So because we're looking for the shortest possible time that he could do this in, we want to optimize that. If we can get an equation in terms of t, then we can differentiate it and set it equal to 0 to find the minimum of t. Sorry, when I talk about t being the time to complete. Now to work out time, that's the distance divided by the speed. Now let's call this first distance here a lowercase x. Then xy will be the square root of 30 squared, which is 900, plus x squared. So the time he takes to complete that portion will be the square root of 900 plus x squared as the distance, divided by the speed, which we'll just call s at this time. We don't know his speed at the moment. Then the second section here, it will be 200 minus x. So the speed he does that bit in, the time he takes to do that bit will be his distance divided by the speed on that section. Now we're told on that section he can run twice as fast as he can swim, so the speed there will be 2 lots of s. Now s is a constant. It's not some variable in this thing. It's a fixed speed that he can swim at, and he can run twice as fast as that, whatever number that is. So that means that we can actually differentiate this as it is. We can do dt by dx, thinking of s as just being a constant we don't know at this stage. If I rewrite this one to the power of a half, that makes it a little easier for me to see the differentiation that we're doing. So differentiating, we're going to have a half 900 plus x squared to the minus a half times by the derivative of the inside, which is 2x, still over s, it's just a constant. So it's like having 1 over s in front of it. If we differentiate the second term, we just get minus 1 over 2s. Tidy that up a little. That 2 cancels with that 2 there. We'll have, it'll be an x on the top, we've got an s on the bottom, and then a square root of 900 plus x squared minus 1 over 2s. So now we've got an expression for that derivative. We can use optimization to find the shortest possible time. We want to set this equal to 0, set the derivative equal to 0 to find maximums or minimums. So x over s root 900 plus x squared will be equal to 1 over 2s. So we'll have 2sx is equal to s root 900 plus x squared. Now that s's cancel through, we don't even need to know what the speed was. We can square both sides. We've got 4x squared is equal to 900 plus x squared. So 3x squared equals 900. So x will be 900 divided by 3 is 300, so it'll be the square root of 300. 17.32 meters. So going back to the context here, he should aim to hit Y at 17.32 meters along the bank. Okay, hope you found that useful. If you did, please like and subscribe. It helps others to find the video too. And go and check out what else is on my YouTube homepage. There's lots of worked solutions for these practice external assessments, plus a whole bunch of other tutorials and videos. If there was anything that came up within these worked solutions that you think, oh, I really have no idea what was happening there, go find a video on my homepage with the title of that thing, and I'm sure that you will find something useful. Otherwise, drop a comment below and I will be happy to point you in the right direction. Thanks. Bye.